Let's start from the top. So, why this whole paper is about? I mean, these notes are about quantum fidelity, right?
Mm-hmm.
So it's about how similar are two quantum states.
Yeah.
And when we talk about how similar they are, it's about the information in the system, like stuff we can measure, like momentum, energy, that kind of stuff, right? Like how similar these two are.
Yeah, I think in this way, we can even make it simpler and
Okay.
just focus on statistics. So
Okay.
we can make it more abstract and just say something like, when we say information in a quantum state, we're talking about something like a random variable, where a random variable is just a set of possible outcomes and a set of probabilities associated with each outcome, such that the sum of the probabilities equals one. So it's
Okay.
just like flipping. So in other words, it's just the generalization of the idea of flipping a coin. You have
Okay.
a coin, and say it's not a 50-50 coin, and say
Okay.
it's like an 80-20 coin.
Mm-hmm.
So it has so what you have is a random variable would be it can land heads, it can hand tails. There are two possibilities, and then
Mm-hmm.
the probabilities would be 20-80.
Okay.
Um, and when I'm talking about information of quantum state, it's the case that the way quantum states function is, I would say, they're a bundle of statistics, because the mathematical structure is that you have the quantum state, which is a vector and Hilbert space. So if you ever hear someone say it, like the vector and Hilbert space, and hold on, let me get the dog out of here. I got rid of that toy. Sorry, Murphy. He's gonna be bored now. Now he's trying to bite me. Hey, hey, hey. Now he's trying to use me as a chew toy. What was I saying? Yeah, so it's a bundle of statistics.
Mm-hmm.
So you have the quantum state itself, and then you have observables.
Yeah.
And these are Hermitian operators. So if you remember from quantum, these are Hermitian operators, and so
Mm-hmm.
these are the set of possible outcomes. So if you have, like, it can be up or down. So if you're saying, like, okay, well, the observable associated with this is that I make a measurement of this, and it can either measure up or it can measure down.
Yeah.
Yeah. And so each one of those basis vectors, you can take one of them and you can apply it to the quantum state, and it spits out a probability.
Yeah.
And so when you look at a spectrum, so when you look at an observable, the set of all of its possible outcomes creates a spectrum. And so if you apply each one of those possibilities to the quantum state, then that would be like your random variable, like the possible outcomes, and then the application of it are the probabilities, and that's given by the Born rule, which is one of the fundamental postulates of quantum mechanics.
Yeah.
So essentially, what you have is this thing for which you can drag out a bunch of random variables. Like, depending on your observable, you can create a classical random variable. And so when I say the information contained in a quantum state, because there are all these different observables and all their bases span the space in a different way, all of these observables are algebraically related to each other. And so the space of information of the quantum state is the space of all of the classical random variables that can be generated by applying the bases of the observable to the quantum state.
Okay.
Does that make sense?
Yeah. This is what gets me confused, because sometimes there's like classical statistics that are in quantum mechanics.
Yes. Yes.
So it's like, yeah, that's what I'm trying to wrap my mind around. Like, what makes it quantum in this case? That's not just like statistical, like classical statistical mechanics.
What makes it quantum is like the structure of this vector and Hilbert space. Like the mechanics that I just described to you,
Mm-hmm.
those are the quantum mechanics. Like those are, and so what makes it quantum, I would say, like, I remember my friend Shelton once said that information theory is applied probability theory,
Yeah.
and quantum information theory is algebratized classical information theory, and it's the algebraic structure. That's what makes it quantum. It's the algebraic structure.
Mm-hmm. Mm-hmm.
It's the fact that you have, for these observables, you can do a change of basis.
Yeah.
So I can take a quantum state and I can represent it in the
Yeah.
position basis, or I can represent it in the momentum basis.
Yeah. Yeah.
And then there's a Fourier transform that allows you to go from one representation to the next.
Mm-hmm.
It's the different it's the algebraic structure of the space that allows for basically the capacity to interpret
Yeah.
the and so what really makes it quantum then is that now that you have this idea of these different languages, these different bases, like if you take the Pauli spin matrices,
Yeah. Yeah.
so you can measure spin in the z direction, the x direction, the y direction. What really makes it quantum then is the fact that you have a Heisenberg uncertainty principle.
Okay.
And so what that means is that if I'm going to measure the spin in the z direction, and then I want to measure it in the x direction, then if the state is along the z direction, so we know the state is aligned along the z direction, but I want to measure it in the x direction, the x direction is orthogonal to it. And so with that orthogonality, knowledge or knowing in the z direction turns into full-blown uncertainty and randomness in the x direction.
Mm-hmm.
And so what happens is that the capacity to which you can know something in one direction they're bounded. So you have this bound on how much you can know. So this is the Heisenberg uncertainty principle. So it's the algebraic structure, which then allows for these mutually unbiased bases or the Heisenberg uncertainty principle, which then, like I was saying in the Anton Zeilinger thing, it's like this idea of information being created. Like in the video that I did on my interpretation of quantum mechanics, I talk about the fact that there's only Anton Zeilinger's idea is that for a two-level system, it only has one bit of information in it.
Mm-hmm.
And so one bit of information can give you a correct answer with certainty to one inquiry. But because of the algebraic structure, there are three inquiries. I can make a measurement here, make a measurement here, I can make a measurement here. And so all of those inquiries, because there's only one bit of information, then there's an inherent uncertainty. And that's why when you go from here to here, it goes from knowing to completely random. And that's the fundamental quantum nature.
So he's trying to explain like why the Heisenberg uncertainty principle exists.
Yes.
Okay.
He's trying to explain why there's an inherent level of uncertainty in quantum mechanics, and that's the nature of quantum mechanics. Is it's inherently probabilistic. So it's like we're trying to give an origin for this inherently probabilistic, uncertain nature of quantum.